Hello everyone, today we'll talk about the problem number of good leaf nodes pairs. We have a binary tree and we're interested in leaves that are not too far apart. Specifically, we're given a distance and you want to count the number of pairs of leaves such that the path between them, the shortest path, the simple path between them, has length of at most distance, counting edges along the path. And you have to just return that number, that count of pairs. We'll be satisfied with a solution that is n squared. We'd also prefer a solution that is something more along the lines of n times the distance, because in this problem, distance is smaller. N is to about 1000, distance can be to about 10. So one easy solution to come up with, or maybe not that easy to come up with, but pretty basic, which you can do with most trees, is to convert the tree into a graph and then go from there. So in this case, we can get an n squared solution by first converting the tree to a graph and remembering what the leaf nodes are in that final graph. And now to count the number of nodes that are also leaves and that are distance of at most distance from our node, we can just run a graph search. A BFS is preferable because a BFS will allow us to only look at nodes that are the correct distance away. And we can run that BFS from every leaf and get the result that way. And that'll be n squared because for every leaf we'll be looking at all the other nodes that are at most distance away. So if distance is equal to 10, then we might imagine that at every possible distance the number of nodes doubles because this is a binary tree. So we will reach essentially all the 1000 nodes starting from every leaf in the pessimistic case. So that is the n squared solution. However, this problem is also an opportunity to talk about an approach, about a technique that's not very difficult. It's pretty intuitive, but it doesn't really come up that often. And that is a 3DP, right? A tree dynamic programming, which probably sounds more scary than it actually is. Because a 3DP is simply just recursion on the tree. So you have a node, maybe something above it. You have those two subtrees. So for a 3DP, we want to calculate something in the left subtree, calculate something in the right subtree. And those values that we calculate have to have two properties. We should be able to calculate the final answer based on those values, and based on those values for our root node specifically, probably. But also we should be able to use all those values and combine them together to calculate the same set of values for this whole subtree rooted in the current root. So we don't want to calculate too much, because then it will be difficult to keep that calculation rolling up the tree. We don't want to calculate too little, because we want to be able to calculate the result from those values. So that's why it's dynamic programming, because this is a simple situation where you have a recursive formulation, where you look at what's below you and you combine those results and pass them above. And of course, we don't want to calculate things many times, but in a tree it's very easy, and it can be just implemented by simple recursion. So in this case, we want to calculate the number of good leaf pairs. So we want our function that recurses on the left subtree and on the right subtree to calculate the number of good pairs within those subtrees. And we also want to calculate all the other good pairs in this whole tree, which of course means that this will be pairs with leaves from the left subtree, one leaf from the left subtree, one leaf from the right subtree. Now, is it possible to calculate that based on one or two values that we can calculate? Because typically we'll calculate 1, 2, 3 values for every subtree and combine them to those same 1, 2, 3 values for our root, and they will also be calculating our result. And in this case, I'm not familiar with any idea that will allow us to calculate this particular result, so the number of pairs that have distance of less than or equal to something. But as it turns out, of course, we are not limited to calculating in our recursive function, to calculate in our 3DP, only constant space information. We can have a data structure, and this will be of course a very simple data structure in this case, but we can hold a data structure, hold something that has a non-trivial amount of data in both our trees. Specifically, in order to calculate the number of good pairs, it'll suffice if we can, of course, know the number of pairs in both the subtrees, but also know how many leaves there are in a given subtree at every possible depth. So we'll have depth 0, 1, 2, 3, and so on, and we'll remember the count of them, either as an array or as a dictionary, a counter in my case, because it's the most convenient for things like that in Python. So for instance, we know that in our left subtree there is 1, 0, 2, 0, so 2 leaves at depth 2, 1 leaf at depth 0. I don't know if it's possible specifically in that case, but it doesn't really matter. And of course we can, for instance, if here is the root, we have this edge and this edge on every path between two leaves. So if our distance is equal to 4, we can, for instance, take, if this is a leaf, we can take this leaf and something that's 2 edges deeper on the right. Or maybe we can take a leaf that's 1 edge deeper, and here also a leaf that's 1 edge deeper. So we can use those information and in essence convolve them, so we have those lists, and we will look at those like crosses that have the same distance. And of course we have to, so for instance, because the distance is equal, we've shown here when the distance is equal to 4, we are interested in the distance being less than or equal to 4. So we have to combine this guy with everything that's smaller on the left as well. We can just do that, and the solution will be simpler but a little bit slower, or we can maintain partial sums when we are running the algorithm. And this will be what we'll be implementing, just remembering the number of leaves that are at every possible depth in every possible subtree. So our recursive function, and of course we'll be keeping a global counter, the result, which will modify at every iteration and return it at the end. So our recursive function that will call on the root at the beginning will maintain those counters using the counter class. So if we're at a leaf currently, we return that there is exactly 1 leaf at depth 0. Otherwise, we have some children, so at the left and right subtree get counters for them. And here also, since we recurse, we'll be calculating the result that's contained exactly in one or the other of those subtrees. And now you want to count the number of good pairs. So we will essentially take the depth on the right side, in the right subtree, to go from 0 to the maximum possible distance. So in this case, it'll be distance minus 2, because we always have to count those two edges. And we'll be maintaining the sum, so the number of vertices on the left and on the right that would create a good pair. Actually, we don't have to remember this right sum, and it's not used later in the algorithm. So we can essentially ignore this right sum. We'll be only maintaining the sum on the left. And now, so first we start with all the leaves on the left. So those at distance at most, distance minus 1, at distance minus 2 in this case. And we'll be taking all the nodes at depth 0 in the right subtree. So all the nodes on the left subtree are a good pair with all the nodes, all the leaves at depth 0 in the right subtree, so we add them to the result. And we multiply them together because we want all the pairs to be counted. And now we remove from our sum the deepest remaining leaves, so the leaves with depth that, by increasing the right depth to 1, we now have to reduce and get rid of the deepest vertices on the left, and so on. So we'll be passing again, doing this sort of like convolution, that this guy looks at everything, so we have the sum of everything. Now this guy also looks at everything, but without this one. This guy looks at everything without those two, and so on. So this sum we have at the beginning, and we're removing elements from that sum. And at the end we have to make sure that we return the number of leaves correctly. So that number of leaves is very simple. For distance I, we take all the leaves in the left and right subtree at that depth, and now they are at depth 1 more, because we have come one step up the tree, and in fact we also forget the deepest leaves as a result, and we return that counter so that we can continue calculating the result up in the tree. And that's it.